Hello, everyone. I'm Guarav Goel. I'm an undergraduate at Harvard University, and today I'll be speaking on powerful integers expressible as sums of two coprime fourth powers. I would like to begin by thanking the organizers for, organizing this conference and giving me the opportunity to present this joint work with Professor Elkies, who is also here with us on Zoom. Our paper is based on work that sprang off of a math overflow question that Elkies asked in 2015, and then suggested to me for an undergraduate research project in the summer of 2020. This is my second time attending ANTS on Zoom, and this is my first academic paper to be accepted to a conference. I'm very excited about it, and I'm also very grateful. All right, let's get started. So I would like to begin by stating our results, for which I first recall the following definition. An integer n is said to be powerful if every prime factor p dividing n divides it at least in second power. More generally, an integer n is said to be k powerful if every prime factor dividing it divides it to the kth power. Powerful integers are in some sense the opposites of square free numbers, and they can be thought of a generalization of squares. A powerful integer n can be written as a squared b cubed for some integers a and b, and this representation is unique if b is required to be square free. And now I'm ready to present our theorem, which is the following. The smallest powerful integer n greater than 1 that is expressible as a sum of two coprime fourth powers is this bad boy right here. It's about 3.09 times 10 to the 36. And here you can see its factorization and its expression as the sum of two coprime fourth powers. I would like to draw your attention to the fact that the value b of this number is 17, and that is relevant in what follows. And in fact, we show that this is the only integer up to a slightly higher bound. Further, we propose a candidate for the second smallest such number, which is about 10 to the 60, has approximately 60 digits, and it is this number right here. This also has b equals 17, and the reason for that should be clear in a couple of slides. Further, we give an algorithm using the arithmetic of elliptic curves to efficiently list all such numbers with small b values. And as an example, we use it to go up to this bound here, 10 to the 173, using which we propose a candidate for the smallest such number with b different from 17, which happens to have b 113. All right. Now let me try to introduce and motivate this question a little bit better. The idea is that we can reconsider several classical Diophantine equations with squares replaced by powerful numbers, or more generally, kth powers replaced by k powerful numbers. The k powerful numbers contain the kth powers as a subset of positive density. When k equals 2, this density happens to be zeta 3 over zeta 3 over 2, which is approximately 46%. And if you haven't seen this before, this is a fun exercise in analytic number theory. And we expect, given this, that when we replace squares with powerful numbers in Diophantine equations, that the solutions are more numerous, but only by a constant factor. However, new behavior can arise. For instance, there are clearly no consecutive squares other than 0 and 1, but there are plenty of consecutive powerful numbers. And in fact, you can use Fermat-Pell type equations to produce infinite families of consecutive powerful numbers. Another example I have of what I mean by new behavior is a 3 powerful counterexample to Fermat's last theorem for n equals 3. What I mean by that is FLT3 says that the sum of two coprime cubes cannot be a cube, but it can be a 3 powerful number. And here is one such example that was found using the elliptic curve x cubed plus y cubed equals 9z cubed, excuse me. What we do in our work is we investigate powerful counterexamples to Fermat's theorem on the non-existence of solutions to z squared equals x to the 4 plus y to the 4, which implies FLT4. And I believe it is the only case that we know Fermat knew before conjecturing FLT what we now call the FFT. So what we do is we search for powerful integer n solutions to n equals x to the 4 plus y to the 4 in coprime integers x and y. We expect that it is expected that such numbers are quite rare, that the number of numbers up to a given bound is that bound to the little o of 1. This is in contrast with powerful numbers that are, for instance, sums of squares, because already squares that are sums of squares are more numerous than this value here. Okay, so what we do is we consider twists of this curve x to the 4 plus y to the 4 is z squared, considered by Fermat. And we consider twists of the form x to the 4 plus y to the 4 is bz squared for integers b. And we seek coprime solutions, coprime integer triples x, y, and z on c sub b such that b divides c. We call such a point acceptable in what follows. We show in our work that if the set of rational points on this twist is non-trivial, then in fact it contains an acceptable point. I apologize for the fact that this is not in the version that we submitted to ANTS, and this is work that we have done since, and it will be in the final published version of this paper. The first twist that works is b equals 17, and this has rank 2. The smallest solution on this curve is with 17 dividing z is exactly our candidate solution n1. But to check that n1 is the smallest over all b seems hard. You'll have to search either over all pairs x and y up to n1 to the half, or over all b up to n1 to the 1/3, and process that many elliptic curves, which is still quite daunting. So what do? Before I tell you what we did, I want to spend a couple of minutes talking about why we care about this particular question. So I hope that I've convinced you to some extent that this is a fairly natural question to ask. But more than that, this particular question needs a surprising combination of sophisticated theory and non-trivial computational power to resolve. At least it took us that. Another reason this is interesting is because it involves an application not previously known, to us anyway, of a computation of congruent number theta coefficients by Hart, Turner, Ria, and Watkins, which was presented at ANTS 9 in 2010, which is also when I was 9. And finally, and perhaps most importantly, it's fun. So let me now proceed and tell you how we begin with the search. So if you recall, if I go back a few slides, we would have to, what we do is we look at all b up to n1 to the 1/3. And n1, if you recall, is about 10 to the 36. So we'd be looking at 10 to the 12 b values, naively speaking, but that's a lot of b's. So the first step is to reduce this to certain, what we call candidate b's, that satisfy certain number theoretic properties. So what I mean by that is, let's start with an n that is powerful and a sum of two coprime fourth powers. The first thing to observe is that every prime dividing n is 1 mod 8. And this is elementary number theory. And so I'm not going to talk too much about the proof, but this already says something about the b's that we're interested in. So already we're only interested in square free b's that are products of distinct primes, all 1 mod 8. Secondly, there's this theorem attributed to Luca, which says that if n is written as a squared and b cubed, then a and b are at least 2. And so in light of bullet point 1, they're at least 17. And this one, I'll spend a couple of seconds talking about the proof of. Well, we have b greater than 1 by the same result of Fermat that I quoted a few minutes ago. And the result a greater than 1 is the one that is attributed to Luca. But we give a complete proof in our paper anyway. The idea is that we're trying to say that x to the 4 plus y to the 4 cannot be a cube, because then if it were, then x squared plus or minus iy squared in the Gaussian integers would also be a cube. And this amounts to reducing the problem to showing that these two elliptic curves have rank 0. And that's a computation that is pretty straightforward in MW rank, for instance. So what we do is, so at this point, using Luca's result, we have reduced the search space by a factor of 17 to the 2/3, which brings it down to 10 to the 11. By using the condition that the numbers are square free, that saves us a factor of pi squared, and so brings down the number of b's to 10 to the 10. And then when you add in the condition on primes being 1 mod 8, that brings us down to somewhere close to 6 times 10 to the 9 candidate b values. But in fact, we claim that there is a much stronger restriction that brings us down to about 66 million, i.e. saves us a factor of 100 more, which is the following. So suppose B is a product of k distinct primes, each 1 mod 8, and we look at this particular curve. The first thing to observe is that if C sub B, if the rational points in this curve are non-empty, then by taking one of these rational points as your P naught in the Abel-Jacobi map, C sub B is isomorphic over the rationals to its Jacobian, which is shown right here. Now, one thing to observe is this curve has complex multiplication. This will be relevant in what follows. The next thing to observe is that the rational torsion of E sub B is just the 2 torsion, all of which happens to be rational. It is the point at infinity plus all of the 2 torsion points. And therefore, we conclude that C sub B has a non-trivial rational point if and only if its Jacobian E sub B has positive arithmetic rank, which happens if and only if 2B is a congruent number. And now that is a serious restriction on B. And in which case, by a result of Coates and Wiles, E sub B has positive analytic rank as well. And this can be checked via Tunnel's criterion, for instance. Now, under the BST, we know that a curve has positive arithmetic rank if and only if it has positive analytic rank, but we don't actually need the BST, the Birch-Swinton conjecture, for what we prove. Okay, so given this, we are reduced to looking at square free B with each factor 1 mod 8 such that 2B is congruent. And there aren't, relatively speaking, too many of those. Further, Lucas' result says that if you go up to a bound M, then going up to M can be used to find all solutions up to 17 squared times M cubed. Fortunately for us, the list of all such numbers, more precisely of all such B, such that E sub B has even positive analytic rank up to 2B equals 10 to the 12, is included in the results of a recent computation by Hart, Torneria, and Watkins that I referred to earlier. And we thank Mark Watkins and William Hart for making this list available to us. And this reduction then leaves us with a little over 66.5 million candidate B values. And looking at these suffices to go up to a bound greater than N1, which is indeed the bound that we mentioned in our theorem. Okay. Now we've reduced the number of candidate Bs, but I still have to tell you how we find solutions for any given B. For that, I'll quickly explain our principal search strategy, which is as follows. Let B be as above. We're looking at coprime solutions to this equation. We start by factorizing this equation in the Gaussian integers. Then we know that X and Y cannot both be odd because of elementary number theoretic reasons. And this tells us that X squared plus or minus IY squared and Z join I are coprime, which allows us to write X squared plus IY squared as beta times zeta squared for beta and zeta Gaussian integers, primitive of norms B and Z respectively, where by primitive, I mean that the real and imaginary parts of this Gaussian integer are coprime, have GCD1, or equivalently that this point is visible from the origin in the complex plane. Now, we write beta as mu plus I nu and zeta as R plus IS. And then we reduce to solving these two conics. For which what we do is, okay, let's start over. Let B be a number as before. There are 2 to the k primitive beta of norm B that we need to look at up to units. For each such beta, look at these two conics. If either is locally obstructed, then this beta cannot give us rise to any solutions. Else, by the Hasse-Minkowski theorem, we have a rational parametrization of this conic. And so we can take a triple RSX of homogeneous polynomials of degree 2 in 2 variables, m and n, over the integers. That's what this subscript 2 means. And you can take this triple to parameterize your rational curve. The problem, though, is that this is not sufficient. Even if you, at least when you plug in integer values from m and n, this is not sufficient to produce all integer triples on this curve, because the R and S, for instance, need not be coprime. Let me explain a little bit better what I mean by this and what the problem is. But the idea is, suppose we begin with Q, which is a quadratic form in 3 variables over the integers, such that the conic defined by the vanishing of Q is nowhere locally obstructed, i.e. has rational parametrization. Then usually a single parametrization by a triple of homogeneous degree 2 polynomials does not suffice to list all coprime triples of integers on Q by using only coprime integers m and n. This is unfortunate. For instance, take Q to be x squared minus r squared minus s squared, the Pythagorean conic. It is well known that this admits the parametrization m squared minus n squared, 2mn, m squared plus n squared. But you can't get the point 4, 3, 5 on this Q by plugging in m and n integers into this formula. This is a little unfortunate. So what do we do? Well, we show that while a single parametrization need not suffice, a finite list still does. So we show that there is a finite list of parametrizations such that every pairwise coprime triple of integers satisfying Q can be obtained from one of these parametrizations by plugging in coprime m and n. And the idea is to look at, for each prime L, you look at the L-adic components of the curve Q, and you only really care about the primes dividing the discriminant, and you work with these L-adic components to produce these parametrizations. Elkies has written a GP routine called QSolve that, given a quadratic form Q, produces such a list of parametrizations. This list is not canonical up to GL2Z, but the documentation of QSolve is currently in preparation. And I'm sure Professor Elkies will be happy to talk more about that. So coming back to our principal search strategy, what we do is we've got these two conics we're looking at. We parametrize one of these conics. We produce this final list of parametrizations as above. In our case, the discriminant is just 4b. So 2 to the k parameterization suffice, where k as before is a number of primes dividing b. For each I, you plug in this parameterization into the other conic. And so that gives you a point on the elliptic curve y squared equals psi I of t comma 1, on which we can run Stoll's hyper-LDAC points. So this is our strategy. Find all beta, find all parametrizations, and all points on this latter curve using hyper-LDAC points up to a calculated height bound, which is in the paper. And this strategy suffices to prove the theorem. If you attended Professor Fisher's talk from yesterday, you will recognize this as basically being two descent on this elliptic curve. Okay, so this proved the main theorem. I want to spend a couple of minutes now discussing another strategy that illuminates the structure of acceptable points, what we call acceptable points on the curve, and which is the other strategy we use to come up with our solution in the first place. So here's the second strategy. For a b at least one as above, we consider the curve E sub b prime, which is 2 isogenous to E sub b, and is given by this equation y squared equals x cubed plus b squared x. Now, the great thing about this 2 isogenous curve is that it admits a map from CB to E sub b prime that is given by this expression here, which does not depend on the existence or choice of a rational point on either of these curves. And this already, as you can see clearly, the image of this map is exactly the set of points capital X comma Y, such that capital X is congruent to B mod a rational square. And so that gives us another algorithm. For each b at least one, you first find all points on this latter curve up to a given height bound, which we explain in the paper. For each such point, check if X is congruent to B mod a rational square. If it's not, just throw it away. And if it is, then recover X, Y, and Z from this, and then check if B divides C. Now, this strategy certainly works for small b's, for which we can find all points on this curve up to a given height. This is, in fact, all we report in the initial paper. But since the submission, we've figured out a more efficient way to list acceptable points on this curve E sub b q prime. So what we do is, and this is not in the paper yet, but what we do is we prove that the set of acceptable points in E sub b prime of q, where again, by acceptable, I mean a point that comes from an integer triple xyz with b dividing z. The set of acceptable points forms a coset of a subgroup of the model way group of index dividing 2 to the k b. And this is kind of important, so I will spend 1 or 2 minutes on the proof. But the idea is that, first of all, the image of rho sub b is a coset to begin with, because x is a wave function for this elliptic curve. What we do is, for each prime p dividing the b, we look at this elliptic curve E sub b prime over the p at x and observe that it has Kodera type 1 naught star and Tamagawa numbers Cp equals 4. Using this, what we can do is we can figure out when a point is p acceptable for each prime p dividing b, and you get a coset of a subgroup of index dividing 2p. And so when you intersect all of these together, you get the number 2 to the k times p. So given this, what we say is, given generators P1 through PR of the model wave lattice, and given a point P, which is an integer linear combination of these guys, we say that this point, we show that this point is acceptable if and only if the coefficients satisfy a few linear congruences, mod 2 and mod P, for each prime P dividing P. And in particular, if you're able to give us generators of the model wave group, then we can use this to list all acceptable points up to basically any given height. Okay, so how feasible it is to talk about the generators of this curve? Well, the Burcham-Swinnerton Dyer conjecture, along with heuristics on the growth rate of the L function of this curve at s equals 1, suggests that the regulators of these curves grow not faster than the square root of p. In our case, the curves have rank least 2, so their model wave groups are typically generated by points of height at most b to the 1/4. This is large enough that we cannot hope to find generators for a typical b up to 5 times 10 to the 11, but a 2 descent in Cremona's MW rank suffice to find the full model wave group for most small values of b, say up to b 10 to the 4th. Now the idea is that each of these curves has a rational 2 torsion point, and so MW rank easily found all the relevant principal homogeneous spaces. And for 67 of the 72 candidate B values up to 10 to the 4, all except these 5 here, MW rank was able to find 2 independent points and prove that they generate the model wave group along with torsion. If you're exceptionally good at arithmetic, you'll observe that a lot of these exception values are sums of 4th powers. And we have an explanation for why that is the case, which I can talk about later, perhaps. And the idea is that this allowed us to go up to this bound, 2 to the minus 2/3 times x 400 for all but 5 b values to find the other solutions mentioned on the results page. This bound with x of 400 is basically arbitrary because, once you have the generators, then you can go up to whatever height you want to find all solutions. I actually ran this code on my computer, I think, to go up to x 3000. And so I found all points with at most 1,300 digits, all numbers with at most 1,300 digits. But I think the 400 suffices for illustration purposes. And I will now end the talk by mentioning some ideas that we have for extending these results. So to take our analysis beyond where we take it, we would need either an extension of the Hart-Turner-Watkins result beyond 10 to the 12, which would require extensive computation, but would be of independent interest and could find other uses. It's been a while since the HGW computation came out. Or we would need an extension of Lucas' result on equations of this form to 17 or 41 or 73, some sort of restrictions on what the solutions to these equations look like. Or we could use a complete parameterization of all coprime triples x, y, b, such that x squared plus y to the 4 is a squared b cubed by homogeneous polynomials of degree 12, as Johnny Roberts does in this paper that he published in dem Journal für die reine und angewandte Mathematik in 2004. But this would be excellent because then we would be able to go up to, we'd only have to look up to n1 or n max to the 1/12th. And so we'd be able to go much higher. And to take our second approach further, we would need to find a better way, say using higher descent, of finding generators of the model wave group of this elliptic curve right here, at least in the fairly special case that we're interested in. I know that Professor Fisher is in the audience, and perhaps he has an idea on how to do this already, but that is where I will end my talk. Thank you very much.
Any questions for Guarav? Maybe from Tom. No pressure. Yes.
Can you say something more about the 5 bad small values of B?
Did you hear that, Guarav?
Yes, I did. So the 5 bad small values of B, right here. So for 2 of the 5 of these, we were able to actually just use more computational power to find points, and that was fine. For the remaining 3, they, as you will observe, they are sums of 2 small 4th powers. And now when that happens, that is saying that the curves that we're interested in have 1 small rational point. Now, using some heuristics from the Burton-Swinnerton-Dyer conjecture, we can say something about the size of the regulator of these curves. And so if one of the points happens to be exceptionally small, then we would expect that there would not be another small generator, that the second generator would be relatively large. And this is why we expect NWRAM to have had trouble in finding generators for these 3 elliptic curves. Yeah.
That sounds very reasonable.
Did you hear that?
Tom Fisher can find them.
Any other questions?
May I ask a question?
Yes, please.
Oh, hi, it's Igor Shpavlinsky. Many thanks for your talk. I just have a question. What do you expect to be the truth? Do you expect infinitely many solutions? Because both sets of size square root of x, so naively you expect the intersection is finite.
Right, actually, so we do expect that, and we have shown, in fact, that there are infinitely many solutions, just because of what we did here. Because I claimed on a previous slide right here that, given generators of the model wave group, you can write down a few linear congruences, mod 2 and mod p for each prime p dividing b, such that the points with these coefficients form an acceptable point. And so if there is one solution to these linear congruences, then there are obviously infinitely many. And so we've shown that there are infinitely many solutions. In fact, for each b that shows up, there are infinitely many solutions with that particular b.
So we should give you a low bound on the counting function, I guess.
Yes, we give that bound in a paper.
Okay, yeah, thank you. And do you have any upper bounds?
Open problem.
Okay, thank you.
Good question, though.
If there are no further questions, that's a very on-time moment to move on. So well done on your first conference talk and conference paper. It was excellent. And thank you for your talk again.
Thank you very much.